So we're going to do an example now of a projectile in air. So we have a kinetic energy term, 1/2 m, x dot squared plus y dot squared plus z dot squared. We have a potential energy term that is just mgz. And we will have a dissipation function that we write as 1/2 alpha x dot squared plus y dot squared plus z dot squared. So it's a uniform medium. So these f coefficients just reduce down to a constant, and the dissipation function is just given by the quadratic terms in the velocities only, without cross terms. So my Lagrange equation, we'll write it down for completeness. d by dt di L by di Q alpha dot minus di L by di Q alpha, and then it's a plus di D by di Q alpha dot equal to 0. And now we proceed. So we'll first consider the x component. So di L by di Q alpha dot is just an mx dot. Di L by di x is 0. And di D by di x dot is an alpha x dot. And so when I form the equation of motion for the x component, I have a mx double dot plus an alpha x dot equal to 0. And now I can just solve this for x dot. So this is m dx dot by dt plus alpha x dot equal to 0. And so I can rewrite this and solve it. I'll have an integral of dx dot over x dot, and that will be minus m over alpha integral of dt. If I'd done that, no, it's alpha over m, isn't it? Alpha over m. So solving, I get a logarithm, natural logarithm of x dot is minus alpha over mt plus some constant, and then I can easily solve for the velocity, integrate again to get the position. And the constant c is determined by the initial conditions. And I would have exactly the same form for the y component because there's symmetry here between x and y. And so I won't bother doing that, but I end up with exactly the same kind of expressions. So the difference will come in then for the z component, and we'll do that next time.